All right, welcome everybody to today's String Venus seminar series. We're very happy to have Anthony Ashmore from Chicago as our first speaker, and he will tell us about exactly marginal deformations and their supergravity duals. Please go ahead, Anthony.
Thanks very much, Fabian. So today I'm going to tell you about some recent work on understanding the moduli of flux compactifications, focusing particularly on supersymmetric AdS5 solutions of supergravity that correspond to the conformal manifold of deformed n equal to 1 4D conformal field theories. And hopefully the outcome will be to show how field theory data like the superpotential is captured by the dual geometry, and how you can derive new results for the field theory, such as counting the number of chiral operators in these deformed field theories. So this is work in collaboration with Dan Waldron, Michaela Petrini, and Ed Tasker. Ed Tasker was a fantastic PhD student who very sadly died just over 2 years ago now. So we sort of hope that getting this work out will really pay tribute to his memory and the great work he did on these projects. So my motivation is going to be 4D n equal to 1 superconformal field theories with type 2b duals. And of course, the canonical example is just type 2b on AdS5 cross S5, which we know is dual to n equal to 4 CP_angles. More generally, however, we can turn on all the fluxes on this background, and then we just have type 2b on AdS5 with some general internal manifold M, which will be dual to some n equal to 1 superconformal field theory. And of course, finding general solutions on the left-hand side here is very hard. Special solutions are known. So for example, with just the metric and the 5-form flux, we know that the internal manifold has to be Sasaki-Einstein. And there are examples with all fluxes turned on, such as the Pilch-Warner solution or the beta deformation of Luna and Maldacena. But this is really just a handful of examples that we know, and the general problem is very difficult. So for some inspiration, let's look at the dual field theory. So if we consider n equal to 4 CP_angles in n equal to 1 language, we get 3 chiral fields phi I with some SU3 flavor symmetry and a non-trivial superpotential that's just cubic in the chiral fields. The F-term conditions from the superpotential just imply that the phi I commute, so they just commute in this way. And so the chiral ring, so the ring of chiral operators, is just the same as the ring of holomorphic functions on the cone over the 5 sphere. So that's just C3. So in particular, the chiral ring are operators of this form, single trace operators of the chiral fields, where the Fi here are symmetric in their coefficients. There's a nice way to capture this counting of these chiral fields up to the F-term relations in something called a Hilbert series. And this is just a graded count of these single trace mesonic operators graded by their R charge or their conformal dimension. So here nk is the number of chiral fields at conformal dimension k. And in this case, for n equal to 4 CP_angles, which is dual to this S5 solution, you can calculate the Hilbert series, and it's just given by this expression here. And from the supergravity perspective, you can count these chiral operators, and they'll just be dual to some Kaluza-Klein modes on the S5. And you can compute these by computing certain harmonic modes on the S5. More generally, however, we know that superconformal field theories come in continuous families related by turning on exactly marginal couplings. So for example, there are deformations of n equal to 4 that preserve some supersymmetry that are given by turning on a superpotential of this form here, where now Fij, are arbitrary complex couplings. They're symmetric in Ij and k, so there are 10 complex degrees of freedom, which gives you the 10 marginal couplings in this theory. Not all of these couplings will define conformal field theories when you turn them on and look at quantum corrections, and you get some conditions on the couplings which come from the one-loop beta functions. And it just tells you that this certain combination of couplings has to vanish. There's a very nice way to interpret this due to Call and Green et al., which is just that you should think of this thing as being the moment map for the SU3 symmetry, and then the conformal manifold, which is spanned by the 2 exactly marginal couplings that survive this constraint. Is locally described either as a symplectic quotient of the space of couplings by the SU3 group, or a Kähler quotient of the space of couplings by the complexified group SL3C. And we're going to see the same structure appearing in the supergravity very soon. So at the n equal to 4 point, we can always choose to write this deformed superpotential in terms of just the 2 exactly marginal deformations, F beta and F lambda. And now the F-term relations one would derive from the superpotential define a non-commutative algebra of Sklianin type due to Ginzburg. If you then want to count the chiral operators in this deformed field theory for generic F beta and F lambda, these are related to computing a certain cyclic homology of the non-commutative algebra. And this was computed in a slightly different circumstance by Vanderberg. And you can compute the Hilbert series that counts this tower of chiral operators up to the F-term relations, and it's given by this result here. So again, at conformal dimension 3, you have two operators, and these are just the two marginal operators that parameterize the conformal manifold. And sort of the key takeaway from this is that in general, it's not now known how to do this kind of counting for deformations of arbitrary n equal to 1 conformal field theories. This is sort of the only case where we know how to do it in general. And what I'll tell you is how to do this for arbitrary Sasaki-Einstein backgrounds and deformations of them, and how to do this from supergravity. So the question I'm interested in is really, can we understand the dual geometries to these deformed field theories? The supergravity solutions will still have S5 topology, but they'll be all supersymmetries turned on, so they're going to be difficult to find. In the case of F lambda is 0, so we turn off one of the superpotential couplings, this is just the beta deformation of aluminum and Maldacena, and you can find the exact solution effectively because it preserves some U1 squared isometry. In the generic case, there are no isometries other than the U1R, which is dual to the R symmetry of the conformal field theory. So you're sort of out of luck and it's sort of unclear how to find these solutions. In the S5 case alone, there's a perturbative analysis due to Aharoni and his collaborators, but again, the full solution is not known. So we really know very little about these supergravity solutions. Even if we can't understand the dual geometries completely, you might also wonder how we count the chiral operators in the supergravity. And you know, the field theory picture is very simple. You just need the superpotential. It's the cyclic homology of some algebra. How do you do the same kind of counting in the supergravity? And I'll tell you how to do that. So the goals of the talk are the following. I'm going to describe the supergravity analog of the holomorphic data encoded by the superpotential in the dual field theory. And I'll then tell you how this holomorphic data determines the full supergravity solution up to the action of some complexified group of diffeomorphisms and gauge transformations. And then finally, using this data, I'll tell you how to compute these towers of chiral fields and compute the Hilbert series for these deformed field theories from the dual geometry. And these are going to be new results for things like deformations of T11 and so on. And this is all really a question about how you calculate the moduli and how you calculate towers of KK modes for general flux compactifications. So that's going to be the sort of takeaway from this. So that's sort of the field theory setup. Now I'm going to tell you about how you think about supersymmetric AdS5 solutions in type 2b supergravity, in particular through the lens of something called generalized geometry. So the supergravity setup is the following. I'm going to consider generic type 2b solutions preserving 8 supercharges with all of the supergravity fields turned on. And these are going to be warped compactifications of AdS5 with some internal 5 manifold M. For a general background, so just some general background, the only symmetries you have knocking around are diffeomorphisms on the internal manifold and p-form gauge transformations. And I'm going to call these collectively generalized diffeomorphisms as sort of a shorthand. So these just give you, the usual p-form gauge transformations of your p-form potentials. If we're looking for supersymmetric solutions to supergravity, obviously we need in vacuum, the fermions vanish and the supersymmetry variations of the fermions also vanish. So this gives you 2 conditions. One is just the existence of a nowhere vanishing spinor that I've called epsilon here, and that's going to be stabilized by a USP6 group. The vanishing of the supersymmetry variations then give you differential conditions on this nowhere vanishing spinor. And these things here are just usually known as the killing spinor equations. So in a very simple example, in the case when you only have metric and 5-form flux, this gives the internal manifold a Sasaki-Einstein. And the geometry of the Sasaki-Einstein can be defined by some nowhere vanishing tensors, a 1-form sigma, 2-form j, and another 2-form omega. And these things can be defined entirely as spinor bilinears in terms of the invariant spinor that characterizes the supersymmetry. Using these objects, you can then construct a nowhere vanishing vector field xi, which you should think of as characterizing the U1R symmetry of the dual superconformal field theory. Constructed from the spinor bilinears, these tensors automatically solve some algebraic conditions, which I've just written down here. And these algebraic conditions guarantee that this set of tensors is invariant under an SU2 instead of the GL5 acting on the internal manifold. In other words, the non-vanishing spinor on the internal manifold defines an SU2 structure in 5 dimensions. So those are the algebraic conditions from the nowhere vanishing spinor. Supersymmetry also implies differential conditions on those invariant tensors. And I've just written down those conditions here. So you get differential conditions on sigma, j, and omega, and it also completely determines the 5-form flux for the solution. It also tells you that this vector field psi is a killing vector, and it generates the U1R symmetry of the background. And sort of geometrically, this just corresponds to an SU2 structure on the internal manifold with singlet torsion. And if you find a set of solutions to this set of conditions, then you know you have a good supersymmetric AdS5 solution. So if we're looking for supergravity duals to these deformed field theories, we expect all of the fluxes to be non-vanishing. They're not going to be Sasaki-Einstein, so they're going to be difficult to find. Of course, there's a very long history of using G structures and generalized geometry to analyze supersymmetric flux backgrounds, and there are too many references for me to write down here. In the generic AdS5 case, as I mentioned, the spinner, the nowhere vanishing spinner, actually defines a USB6 structure, and I'll just refer to the structure as being an exceptional Sasaki-Einstein space. So this is all very sketchy. The thing to sort of take away is that, again, this invariant spinner defines some nowhere vanishing tensors, which I'll call X and K, and X and K effectively characterize the hypermultiplet and vector multiplet degrees of freedom of the AdS5 supergravity if you compactify it on these spaces. These things are tensors in E66 generalized geometry. So this is just some generalized geometry where the relevant group is some real form of E6. And this is the one that's relevant to type 2b compactifications down to 5 dimensions. X and K are just tensors of this generalized geometry, and you just construct them as irreducible representations of the relevant E6 group. So the sort of key takeaway is that you have this invariant spinner. It defines a pair of these structures, and each of these structures individually defines some G structure. So K, for example, is a generalized vector. It lives inside the generalized tangent bundle E, and it defines an F4-4 structure. Oops. X here is a complex section of the adjoint bundle. It defines some SU*6 structure. And together, you want these things to intersect on a USB6, because that's the USB6 that the invariant spinner for the background generically defines. Given two of these structures, X and K, they will intersect on a USB6 if they also solve some compatibility conditions, such as the action of X on K is 0 and a certain normalization conditions. And you should think of these as being the analog of the algebraic conditions that I wrote down for the Sasaki-Einstein background. And then sort of the key to this is that if I give you X and K, it's completely equivalent to me specifying all of the supergravity fields for the solution. So if you can find X and K that solve these algebraic conditions and the supersymmetry conditions I'm about to write down, you've found a supersymmetric background. So in the simplest case of Sasaki-Einstein, the structure was defined by these tensors sigma, j, and omega. You can very explicitly write down what these K and X structures are. In particular, K characterizes the contact structure of the geometry. So it's written in terms of this vector in this 3-form here in this way. And the X structure defines something called a Cauchy-Riemann structure, which is again a doublet of 3 forms constructed from the tensors on the underlying Sasaki-Einstein. And this also contains information about things like the complex axiodilaton. So up to now, I've just told you about the algebraic conditions that these backgrounds generically satisfy if they're going to be supersymmetric. Obviously, supersymmetry imposes differential conditions on these objects as well, just like the exterior derivative of those invariant tensors for Sasaki-Einstein. And the key to finding these differential conditions is to think about how symmetries act. So symmetries act in generalized geometry via a generalization of the Lie derivative. And you take this Lie derivative along some generalized vector field, which I've just called V here. And V has some vector component, some 1-form components, some 3-form components, and so on. And this is such that the generalized Lie derivative effectively does a Lie derivative for you and also a gauge transformation at the same time by these 1 forms and 3 forms. So in other words, this Lie derivative generates the group of generalized diffeomorphisms, which is just diffeomorphisms and gauge transformations. Supersymmetry of the solution is then equivalent to some differential conditions on these pair of structures X and K. And the supersymmetry conditions are just given by this sort of odd-looking collection of conditions here that I won't really go through in much detail. This just says that K is something like a killing vector for the solution. X has to be charge 3 under the U1R symmetry of the background. And then these mu's come from a triplet of moment maps for the action of generalized diffeomorphisms on the space of all X structures. But for us, all this means is that you have some extra differential conditions that you have to satisfy for all generalized vectors V. One can show that these are equivalent to the general supersymmetry conditions for an AdS5 background, so an arbitrary AdS5 background. And this also shows you that the lead derivative along K is what's generating the U1R symmetry of the dual superconformal field theory. And all you should really take away from this is that this generalized geometry gives you a very nice way to package sort of the field theory data of the dual CFT. So that was sort of a lightning review of n=1 field theories in 4 dimensions, and the kind of field theory properties one might be interested in calculating, such as the superpotential or counting chiral fields. And we also started thinking a little bit about how those might appear in the dual supergravity geometry. I then told you a little bit about a nice formalism for describing general supersymmetric flux backgrounds in type 2b, which is very well suited for characterizing hypermultiplet and vector multiplet degrees of freedom. So what we're going to do now is use this to understand the supergravity analog of the superpotential in these field theories, and also use this kind of language for counting chiral fields in the dual field theory. So first of all, one might wonder if we can solve for the general supergravity solutions that are dual to these deformed field theories. And the answer is just that this is very unlikely. It seems very unlikely in general. So solving for the general solution seems pretty intractable. These backgrounds in general will have no isometries after the deformation. And the system of partial differential equations you find is in general going to be harder to solve than something like the Mondrian-Paire equation for Calabi-Yau that we're all still, fighting with. Instead, we want to know what the closest we can get to the full solution is that we can solve exactly. And the idea is to focus on a subset of those supersymmetry conditions that give you something like a set of holomorphic conditions. So they specify some holomorphic data. And in particular, we're going to focus on this subset of conditions here. So we've dropped that third moment map mu3, and we just look at these conditions. And what we'll find is that solutions to these conditions are sufficient to then argue that a full solution exists, and solutions to these conditions are enough to do things like count chiral fields in the dual superconformal field theory. So this set of conditions defines something like an exceptional Sasaki structure where we drop the Einstein, and they roughly translate to having an n=1 theory, an n=1 field theory that's supersymmetric, but isn't conformal. And then finding the full solution is going to be something like a renormalization group flow to solve the last remaining condition. Importantly, the space of these geometric structures X that solve these conditions is scalar, so that gives us some nice geometry. And the final supersymmetry condition, this third moment map, is effectively given by imposing the moment map and then quotienting by the symmetry group, or equivalently, we can just quotient by the full complexified group directly. And we're going to use this to argue that these solutions exist. So much of this is sort of a very general argument that works for general backgrounds, but I'll just focus on doing this for deformations of Sasaki-Einstein backgrounds. So if we can find a deformed solution to these holomorphic conditions that I'll call X star, you can show that a full solution must exist that solves all the supersymmetry conditions. So this shifted moment map here is just the moment map for diffeomorphisms and gauge transformations, but now with fixed K. To linear order, the exact solution you find X star to this holomorphic to these holomorphic conditions matches the infinitesimal exactly marginal solutions that one can find perturbatively. And this then implies that there is an open subset of stable points that lie on orbits under the action of the complexified group that will intersect the surface where this moment map here vanishes, and this guarantees you have a full solution. So all of the X star that you find are stable and give full solutions. And the nice thing about this is that different X stars flow to different solutions unless there are isometries, which completely agrees with the field theory picture that we saw earlier, where there was a difference between exactly marginal and marginal deformations. So the picture you should have is very familiar from many supersymmetry problems. You first solve some F-term conditions, which are holomorphic, and then you impose some D-term constraints, which can be done either by a symplectic quotient or quotienting by the complex group. So here I've just drawn the space of X's. What we're going to do is find an exact solution for X star, a deformed solution that's dual to these deformed field theories, and then argue that the action of the complexified diffeomorphism and gauge transformation group puts you onto honest solutions to the supersymmetry conditions. And the physical interpretation of this is as follows. It's the orbit under the action of this complexified group that fixes the superpotential of the dual superconformal field theory. Providing these X's are charge 3, that corresponds to doing a marginal deformation in the dual field theory. And then motion along this orbit is basically renormalization of the Kähler potential in the field theory.
Anthony?
So just as sort of a concrete example, let's see how this works for S5.
Anthony,
There
you
we
have
had this map
5 minutes.
between, thank you. There we had this map between single trace Masonic operators and holomorphic functions on the cone. These are captured by deformations, which are cubic. And in the S5 case, these are just cubic functions of the coordinates. And at the S5 point, we wrote down this exact solution for X. And we want to know how to deform this by a cubic function F. One can find a new exact family of solutions to the holomorphic conditions, which I've written out sort of explicitly here. Here, BI is a form and VI is quadratic in the deformation. And these are all known exactly. In the S5 case where F is cubic, this reproduces the perturbative calculation. In the case where F is just this particular cubic function here, you can solve for the explicit symmetry transformation that takes you to the exact beta deformed lunar Maldacena background. But in general, this, and also this works for any deformation of a Sasaki-Einstein background, because all we used was the underlying Sasaki-Einstein structure. So what can we do with this partial solution? Well, X star fixes the superpotential, so it should encode the space of Masonic operators. And you can count these graded by the R charge in the supergravity to give the Hilbert series. This counting was done at the undeformed point by these authors previously, but we want to do this counting now for the deformed field theories. So what we want to do is count deformations of X up to the action of the symmetry group, and this just defines a cohomology which counts the chiral operators for us. So it's just solutions to the mu plus moment map modulo symmetry transformations. And here we drop this condition that X is charge 3, so we can count the full tower of KK modes. And importantly, this counting only depends on the class of X under the action of the symmetry group. So we don't need to find the full solution, the full supergravity background. We can use the solution to the set of holomorphic conditions to do this counting. So this is easiest to present when the deformed solution is generic in some sense. All this means is that the one form, which is the exterior derivative of the function that parameterizes the deformation, is nowhere vanishing. And this corresponds to the case, for example, where F beta and F lambda in the superpotential are non-vanishing. In this case, the cohomology that counts these chiral fields then reduces to this cohomology here, some Lie algebroid cohomology defined using this non-vanishing one form. And you can actually compute this using something called the Cohen-Rossi cohomology of the original Sasaki-Einstein space. So these deformations give the chiral deformations in the field theory. You can then solve for the Hilbert series that counts the chiral operators. And very generally, for any of these deformed field theories around a Sasaki-Einstein point, you get the following result, where this I here is just a single trace superconformal index, which can be computed at the original undeformed point. So for example, for field theories dual to deformed S5s, so deformed n equal to 4 super Yang-Mills, with an arbitrary superpotential that's captured by this generic cubic function, the Hilbert series can be expressed like this here, which is in complete agreement with the counting of this cyclic homology of this algebra in the field theory, this non-commutative algebra. That was already known. You can also derive new results for Sasaki-Einstein, for field theories dual to deformed Sasaki-Einstein backgrounds, such as T11. So T11 is just a U1 bundle over P1 times P1. The field theory is known. It's the Klebanov-Witten theory with an SU2 times SU2 global symmetry. And in the undeformed case, the Hilbert series that counts this tower of chiral operators, this tower of KK modes in the supergravity, is just given by this result here. If you now take the Klebanov-Witten theory and turn on a generic superpotential, so you deform the field theory, it's not known how to do this counting, but you can do this counting using this generalized geometry picture and this solution to these holomorphic conditions. And I've just written down what the answer for this deformed Hilbert series is here. One can check that this matches the explicit counting of chiral fields in the field theory modulo the F-term relations up to some value of K just by multiplying some matrices together. But what's sort of interesting is that there was no previous calculation of this in the field theory, effectively because it's very hard to calculate these cyclic homologies. As I said, you can do this for any Sasaki-Einstein. It only uses the underlying Sasaki-Einstein structure. So you can also do this, for example, for deformed field theories dual to Sasaki-Einsteins of this form, which are just U1 bundles over Del Pezzo surfaces. And these are all new results that weren't known before. So let me sort of summarize. I told you how to solve how the background geometry in supergravity, particularly through the language of generalized geometry, naturally encodes the superpotential of the dual superconformal field theory. And I told you how to solve for the holomorphic data in the supergravity, even for backgrounds with all fluxes turned on. And in particular, you can find an exact solution to this set of holomorphic conditions, and then argue that the full supergravity solution is just sort of a complexified symmetry transformation away. Importantly, you can then calculate things in the field theory that weren't known before, such as these Hilbert series, effectively because those calculations only depend on the class of the structure under the action of the supersymmetry under the action of the complexified symmetry transformations. So just some ideas for the future. Similar formalisms work for AdS5 and AdS4. Compactifications in M theory, where you can think about A maximization or F maximization there. This cohomology that I told you gives a very natural definition of a supersymmetric index for generic flux background, which should tell you something interesting about how to think about moduli for these backgrounds. And finally, A maximization should be very nicely described for these generic supersymmetric backgrounds. In particular, this structure K precisely captures this A anomaly coefficient. Okay, thank you.
All right. Thank you very much, Anthony, for your very nice talk. Are there questions? Okay, so while people are thinking about questions, maybe I can start. So just to make sure that I understood this, the intuition for why the class of the structure determines the spectrum is that you have imposed the holomorphic conditions. You find some solution for that, then you can do a flow which ends at the conformal point. And unless you have some special symmetries, this flow sort of produces, again, a full dimensional solution. I mean, yeah, you're not jumping, and that in this way you can count the, I mean, yeah, you can count the dimension of the solution by just sort of counting the holomorphic solutions.
Yeah, and effectively, yes. So you can argue that it's the class of these structures that encode the superpotential. So it's sort of not surprising that you can count things in the supergravity using only the class of the structure that you could count in the field theory using only the superpotential. So yeah, that's exactly right. Yeah.
Thank you.
Can I ask a question? This map is unique for any given solution of these partial equations. You get a unique full solution.
Yeah. So if the original background you started from, the undeformed background, has no isometries, then you get a unique solution up to the conventional action of diffeomorphisms and gauge transformations. So real diffeomorphisms and gauge transformations. If you have an isometry, then if you do deformations that are related by the actions of those isometries, then those two will flow to the same solution, which exactly matches the field. So in the field theory, you either have some deformations which are obstructed, which you sort of get rid of, or you just say that those deformations were actually the same deformation under the action of the complex group. And in the supergravity, the natural perspective is that second perspective. Those two things you thought were different are actually the same under the action of the complex group.
Thank you. Makes sense.
All right. In the interest of time, we have to move on. So let's thank Anthony again for his very nice talk.